All right, let's take a look at 6.4, special systems. These problems are going to result in something different than what you're used to solving. So you may not get a solution of 2, 3 today. You're now going to be looking at one of these two examples potentially. Now, being able to do this is a big part of section 6.4. This goes back to section 2.4. If you can't realize right from the get-go that this solution is no solution, then you could go ahead and do a little bit of algebra. You would see that 3 does not equal 4, therefore we would have no solution. In a problem like number 2, we would go ahead and distribute the 2. We would get 2x plus 2 equals 2x plus 2. This becomes infinitely many, or the all real number symbol, because anything I plug in for x will equal both sides. Or it will make both sides true. Let's take a look at some vocab for today. I have consistent, a system with at least one solution. I have inconsistent, a system that has no solution. I have independent, a system that has exactly one solution, and dependent, a system that has infinitely many solutions. So take a few moments, look over those, and we're going to do a little oral quiz right now. So let's take a look at this scenario. Could I have a consistent independent? Well, think about it. Consistent meaning what? Independent meaning what? Yes, that is possible. I could have at least one. I could have exactly one. And here's a scenario right here of a system where I could solve that to get a coordinate and ordered pair of my intersection point. Could I have a consistent dependent system? Well, once again, think about what the word consistent means. Think about what dependent means. Yes, I could. At least one. But in this case, infinitely many, which would actually result in the exact same two equations, meaning it is the same line. Third scenario, can I have an inconsistent independent system? Well, think about what these two mean. And that is a big fat no. How can you have no solution but have exactly one solution? Not possible. And the fourth one, can you have an inconsistent dependent system? Once again, a big fat no. How can you have no solution and then have infinitely many? So that would result in an impossible situation as well. Now, last part here, some of you may be thinking what inconsistent lines actually represent. If you have two lines that are inconsistent, you are representing two lines that never intersect. Therefore, they would be, you got it, parallel lines. If you notice they have the same slope here, therefore they would never intersect because they have the same rise over run. So when we talk about inconsistent, that is what we are referring to, parallel lines. Take a look now at some problems. So remember, we're always trying to find that point of intersection. Well, in number 1, if you notice, they have both slopes of 1. Therefore, they are parallel lines. Therefore, they will not intersect. Therefore, there is no solution. Now, if you didn't realize that, let's go ahead and use the circle and drag method. X minus 1 equals x plus 2. Go ahead and, if you still need to, try to solve the problem, and you're going to get negative 1 equals 2, which is not a true statement, therefore inconsistent and parallel lines. So in my class, once you've noticed that the lines are parallel, you can simply say no solution, inconsistent right from there. Like I said, less work is actually more for me. Let's take a look at another one right here. Looks like a standard type of system, but whenever you add x to both sides here, you're actually going to notice that y equals x plus 3 and y equals x minus 4, once again, are parallel lines. Slopes of 1, once again, if you don't realize that, you could use substitution and hopefully see here, negative 4 does not equal positive 3, therefore there is no solution, and they would once again be classified as inconsistent. Next problem we'll take a look at. Not always do you want to isolate variables the traditional way. So you don't have to take 3x away from both sides here and then subtract 2 and so on. What I would prefer you to do in a problem like this is go ahead and actually add y to both sides. And take a look at what you're left with. 3x plus 2 equals y. And your original equation, y equals 3x plus 2. If you notice, these are the exact same equations. So I would then hopefully notice that my solution was all real numbers, because anything I plug in for x for both of these would make them true. Same thing for y. So those points that will all lie on those same lines because they are the exact same line. I could classify this as, take a few seconds, think about it. Yes, jackpot, you are correct, consistent dependent. Now let's take a look at this problem. I thought about some different ways to attack this problem. I would probably go ahead and first of all distribute here, and that would leave you with y equals 4x plus 4. And then down below, I'm just going to carry that on. Now I'm actually going to substitute here again. However, I'm going to substitute in for the x value. So I'm going to take this right here, and I'm going to rewrite the top equation as y equals 4 times y minus 1 plus 4. Took everything for x and dropped it in for x. Y equals 4y minus 4 plus 4. Y equals 4y plus 0, if you want to think about it that way, because that's going to confuse some people. And then I could go ahead and subtract 4y from both sides, and I get negative 3y equals 0. Actually here, some people would then say, oh wait, that's no solution, but in fact, you can divide by negative 3, no problem whatsoever, and y actually ends up being 0. Then take your 0 for y, plug it in, and you would see that 0 minus 1 equals x, and x would equal negative 1. Now, if I take negative 1 and plug it back in, negative 1 plus 1 is 0, 0 times 4 is 0. Take a negative 1, plug it in for x, and negative 1, add 1, y equals 0 as well. So we would see that this problem actually works out perfectly fine. This is like section 6.2. Your coordinate of your point of intersection is negative 1 comma 0. That is your solution. Therefore, we would classify this, if we had to, as consistent independent. At least one, but exactly one. Now, here's a word problem. Matt has $100 in a checking account and deposits $20 per month. Ben has $80 in a checking account and deposits $30 per month. Will the accounts ever have the same balance? And then explain. Well, here's the good news. Anytime you have different slopes and different y-intercepts, your graphs are going to intersect somewhere. If they have the same y-intercepts, that's where they are going to intersect. And that would be your solution. But in this case, if you think about a graph, we got Matt starting higher, we have Ben starting lower, we have Matt rising slower, and Ben rising faster. So these two lines will intersect at some point. So keep in mind, a graph is always an option. However, I think this method is definitely a little better. If you notice, you're going to write an equation for, I already went ahead and did it to save us some time. Here's Matt's equation, and here is Ben's equation. We're going to set it up. Just go ahead and do circle and drag, set up the equation. Subtract 20x from both sides. Subtract 80 from both sides. Divide by 10, and we would see that in 2 months, they would be equal in value. I can take my 2, plug it back in for x, which I did over here, and I see that 2 times 20 is 40. 40 plus 100 is 140. So these two will have the same amount of money in their accounts at month 2, and at month 2, they will have $140 as in their bank account. Now, here's a way to think about solving this mentally. I like to do this a lot because, yes, it's great to be able to set up an equation, but can you actually reason what the problem is asking for? Take a look at 20 and 30. We know that Ben has to make up $10 Matt is going to be $10 lower each month, but he starts $20 higher. So we need to make up $10 twice to make up for that $20. There's that 2, which represents the 2 months. So problems definitely are able to be done mentally. Obviously, we want to be able to set up this system to be able to solve it. Now, here are some additional problems that we could do. Let's go ahead and solve each one of these. For number 2, I'm going to just rewrite this as y equals x plus 1. Right here, I'm going to add x to both sides, and I'd be left with y equals x plus 3. Anyone notice what the solution is immediately with no further work? You got it. parallel lines. We have a slope of 1. Therefore, oops, sorry, that yellow might be tough to see. Therefore, this is, let me write a different color here. Therefore, this is no solution, and it would be classified as inconsistent. Moving over to number 4 here. Maybe divide the top equation by -1, -1, -1, and we get y equals -4x minus 1. The bottom one, let's go ahead and subtract 4x from both sides. Sorry, I'm squeezing it in there, but you get y equals -4x plus 2. Different y-intercepts, which means they cross the graph. One crosses at -1, one crosses at +2. However, if you notice, they do have the same slope. Therefore, the rise over run will be constant, making these two lines parallel. It's going to look, obviously this is a sketch, but it's going to look something like this with your negative slope, and we would have, once again, inconsistent, no solution in this case. All right, here are 2 additional problems. Why don't you take a look at those 2? See what you can do. Go ahead and pause the video, and then go ahead and solve. You notice the first one, number 6, actually works out to the exact same equation. This and this are both the same equations, therefore there are infinitely many. That would be consistent dependent. Number 8 actually works out perfectly like a regular problem. So we solve this, we come out to x being -3, y being 0 for both of those, and that would be then classified as consistent independent. So hopefully, I had a feeling that was it. Hopefully that gives you a little better understanding of section 6.4. Like I said, don't just assume every problem you do is going to be infinitely many or no solution. It still could be your typical kind of problem like we have right here. Go through the math, read the sentence, the system out loud, see if it makes sense. If it does not, something may be up. If it looks like it's solvable, go through and solve using the methods we did at 6.1, 6.2, and 6.3. Best of luck.